All right, guys, so welcome back. We are looking at lesson 1.6 about regression lines. So the goal of today's lesson is to be able to make regression lines that we can use to model data and make predictions about data outside the scope of just what we have. So we make predictions for values that we may not necessarily have in our data set. So let's get cooking. So last time we used this data to create this scatter plot. So this time I'm not going to be walking you through all the data entry and everything again. If you need to, you can go back and look at lesson 1.5 about scatter plots if you need a refresher on that. I will have the directions in here, but I'm not going to be entering the data with you this time. So what we're going to be doing this time is we're going to be taking this data and creating a regression line that goes along with it that we can use to make predictions about the data. So the way we're going to do that is we're going to enter the data just like we did last time. So you're going to press stat, edit, and then enter your data into list 1 and list 2. If there's stuff in there that you need to get rid of, so let's say that you just have a few things entered into another list or into a list that you want to use. In order to get rid of stuff in a list, you highlight the name of the list, so L3, and press clear. Don't press delete, press clear and then enter, and it'll get rid of everything in that list. So let me show you what happens if you press delete. So if you press, in fact, I'll do it with this list. If I press delete, if you noticed, list 2 is gone. List 2 no longer exists. If that ever happens, you can fix it by pressing insert, and then you can tell it which list you deleted, so list 2, and it'll bring the list back. So just make sure that you know the difference between clearing a list and deleting a list. So if you have stuff that's in a list that you want to use again, make sure that you clear it, don't delete it. So now we've got list 1 and list 2. So we're going to quit. We've got our data entered. So what we're going to do is we're going to go back to stat, and this time instead of edit, we're going to go over to this tab that says calc, and we're going to scroll down and we're going to find number 8, which is linreg a plus bx. If you notice, there's also linreg ax plus b. With both of these, you're going to get the same thing. The difference is your a and b values are going to be swapped. So if you do accidentally use number 4, that's fine. Just make sure that you pay attention to what your a is and what your b is. The reason that we use number 8 is because the standard way to write the equations of regression lines in statistics is with the y-intercept first as opposed to the slope first. So we're going to go to linreg a plus bx, and xlist is my explanatory variable, which was our population density, and we have that entered in list 1. Our y-list was our response variable, which is our COVID deaths per 100,000 people. We have that in list 2. The frequency list, we're going to leave blank. And then for store reg EQ, what this means is if I want to actually be able to see the regression equation on the scatter plot, I need to store it as one of my equations. So to store the regression equation, you're going to press vars, and you're going to go over to yvars and choose function. So what this pulls up is these are all of the functions when you press y equals. These are all the functions that you have stored in your calculator. So if we say y1, and then we go to calculate, it gives us some information. So what this gives us, so all these different values are important to this equation. So first we have A. A is the y-intercept, which is about 12.88. We've got B, which is the slope, and that's about 0.13. And then R squared and R, we're going to talk a little bit about in a minute. And R squared is going to be a little bit of a bonus, and I'm going to give an extra video just about, or an extra portion of the video just about R squared after the end. And R is what's called the correlation coefficient. So here was our output. A is the y-intercept. So one thing that we're going to have to do with the y-intercept is interpret it in the context of the problem. Same thing with the slope, we're going to interpret it in the context of the problem. R squared is called the coefficient of determination, which I'll give a little portion at the end of the video about that again. Then R is the correlation coefficient, and we'll interpret that in just a minute as well. So one thing that I also want to point out on your calculator, if you do not see R and R squared, the reason is you have your stat diagnostics turned off. So if you press mode on your calculator and go find where it says stat diagnostics, if you have it turned off, and let me show you what the screen will look like if you have it turned off. So when you do this, if you have your stat diagnostics turned off, R and R squared don't pop up. So then you need to go to mode and make sure that stat diagnostics are on. And now when you enter that information, and I'm just going to walk through doing all of this again. I'm even going to enter the stored regression equation again. Now when you do it, you'll see R and R squared. So another thing that I want to point out, if you're not sure if you actually stored your regression equation, when you press Y equals, it'll have the equation in here. So if you notice, this is Y-intercept, which is that 12.87, all that stuff, plus the slope, 0.12, blah, 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 times X. And X is our explanatory variable. So before we actually start looking at this, we want to interpret these quantities in context. So here's a rough approximation of the regression line. This should really be an approximately equal to sign. I can't type that in this program. So Y is approximately equal to this because we rounded these values. So we're going to interpret these values in context of the problem. I should say quantities. So the first one we're going to talk about is the slope. So this slope of 0.13, in the context of this problem, what the slope actually means is each time the explanatory variable increases by 1 unit, the response variable is predicted to increase by about whatever the slope is. So this predicted to is extremely important because remember, this is just a prediction for the data. This is not going to perfectly fit the data, and we're going to see that in just a second when we look at the graph of it. But so each time, and for our purposes, each time our explanatory variable was population or people per square mile. So each time the people per square mile increases by 1 unit, the COVID deaths per 100,000 people is predicted to increase by about 0.13. So then for the Y-intercept interpretation, what this means is when the explanatory variable is equal to 0, then the response variable is predicted to be about whatever the Y-intercept is. The Y-intercept sometimes in the context of the problem does not make sense, which in this case, if we were to try to put this in the context of our problem, what this would say is when the population density and people per square mile is equal to 0, so there's no people in this area, then COVID deaths per 100,000 is predicted to be about 12.88. In the context of this problem, that doesn't really make sense because if there's no people, nobody could be dying from COVID. So this Y-intercept, it's more of a starting point for the graph. It's more of saying if this were to be 0, you would be predicted to have this. It's sometimes not going to make sense in the context of the problem, and that's okay. That doesn't mean that you're wrong. So we're also going to look at R, which is the correlation coefficient. So what R does, R tells us the strength and direction of a linear correlation between two variables. The word linear is important because there are other types of relationships, but R tells us strictly about linear correlations. So when we interpret R can tell us the strength and direction of a linear correlation. So to tell the strength, we're going to use this right here. Basically, if the absolute value of R is less than 0.4, there is a weak linear correlation. If it's between 0.4 and 0.7, there's a moderate linear correlation. And if it is larger than 0.7, there is a strong linear correlation. Remember, correlation meant as one variable increases, the other tends to increase. We need to be really careful with correlation because correlation does not imply causation. And for example, if we take our situation, our explanatory variable was population density and our response was COVID deaths. Population density alone does not cause COVID deaths. There are other factors that play into it. So that's how we tell the strength. The direction is either positive or negative. And really you can tell this just by looking at R. If R is positive, there's a positive correlation. If R is negative, there's a negative correlation. So in our case, we have an R of 0.79, about 0.79. So for our data, this implies that there is a strong positive linear correlation between population density and COVID deaths per 100,000 people. So now that we understand what all of these variables that this output means, so we have A, B, R, we'll talk about R squared at the end. Now that we understand what these mean, let's practice with interpreting some R's, and then we're going to take a look at what the graph is actually going to look at. So for example, 0.92, this would be strong positive linear correlation. And then I'm not going to write down the rest, but if we work through these, negative 0.74, the absolute value is greater than 0.7, so this is strong. R is negative, so this would be a strong negative linear correlation. This is 0.16, that's fairly low, so there is a weak positive linear correlation. 0.55, that's in the moderate area, so we would say there's a moderate positive linear correlation, and then for this one, there's a moderate negative linear correlation. So we've looked at all of these inputs, we've interpreted some R's. Let's look at our specific data. So first, what I want to look at is our, right here, our regression equation. So this actually, when you get the statistics, instead of Y, you're going to use Y hat. It's Y wearing a little hat. It's just a cute way to describe Y. That's just the way that statistics does it. It's adorable. So we have Y hat, and what that hat means is it's the predicted Y value from this equation. So Y hat is approximately equal to 12.88 plus 0.13x. So when we go back to look at the graph on here, if I have stored my regression equation, when I press zoom 9 to look at my scatter plot, it'll graph the regression equation in the middle of the graph. So what I notice is not every point lies on the line. Obviously, there would be no way for us to draw one line that contained all of those points. But that line does give us some predicted values. So what we can do with this line is we can use the equation of the line to make predictions about data points. So what we're going to do is we're going to take Georgia, which had a population density of 176.4 and a COVID deaths per 100,000 of 45. And we're going to use our regression line. And in case you're curious, that's Georgia right there. And we're going to use our regression line to calculate what's called a residual. A residual tells us how well we estimated, basically. The residual will tell us how much we over or underestimated by. So we know that the actual value of the response in Georgia was 45. So what I want to do is I want to find the predicted value of the response variable in Georgia. So the predicted value is 12.88 plus 0.13 times 176.4, because this is our X value, which was the explanatory, which was population density. So we're going to plug our population density in here for X. And then what I get is about 35.812. So our actual value is 45. Our predicted is 35.812. So to calculate the residual, I do actual value minus predicted. So, and a girl in statistics last year came up with this. R equals A minus P. For calculating residuals, remember RAP. Residual equals actual minus predicted. So what I get is a residual of 9.188. So because this residual is positive, what that means is our actual value is greater than our predicted value. So our model actually underestimated the actual value by 9.188 units. And the units in this case is deaths per 100,000 people. So we have now looked at regression lines, what the regression line looks like on a graph, how to use regression lines to make predictions. So I had told you before that there are some other kinds of relationships that you might see. So what we're going to look at is just a couple pictures of scatter plots that have different relationships. And these are the two other kind of models that you might see this year. And all that you need to do with these this year is just recognize them. So a quadratic model is something that has this U shape. It can either be opening up or opening down, but it's a quadratic model because it actually looks like what's called a parabola. And a parabola is the graph of a quadratic function, which we're going to be talking about later this year. Exponential model is something that either exponentially increases, so starts slowly and then rapidly increases, or exponentially decreases, so rapidly decreases, then hangs along the x-axis. So we're going to study both of those kind of functions later in this course. So that is it for today's mandatory things you need to know. So we talked about writing regression equations, we talked about R, we talked about residuals, and I showed you a couple of examples of nonlinear data. So in class, we're going to go through all of these major topics. But before I finish, I promised that I would tell you a little bit about R squared. So R squared is called the coefficient of determination. And you actually find it. Well, one way that you can find it is by taking R and squaring it. And there is an explanation for why that works. And if anybody wants to know, I can make a separate video talking about just why R squared happens to be R squared. So before we said the correlation doesn't imply causation, but what R squared actually does is it tells us the amount of variation in the response variable that is accounted for by the explanatory variable. So our R squared was about 0.63. And what that means is that roughly 63% of the variation in the number of COVID deaths per 100,000 people can be accounted for by the population density. In other words, this accounts for 63% of the variation. There's about 37% of the variation in the number of COVID deaths that is not accounted for by the explanatory variable. That doesn't mean that 63% of the cause is the population density, but 63% of the variation, the amount of when we drew the regression lines, 63% of the reason that those points do not lie on those lines can be accounted for by the explanatory variable, which is population density. So that is it for this week. If you're a little bit more interested in that, you can ask me about it and I can make another video. But I hope you have a wonderful day and come to class ready with questions. I'll see you in class.